Welcome to Electric Field Strength. Please note that I'm recording this video during a thunderstorm, which I thought was quite apt for this topic. Electric field strength is easiest to learn about if you start by comparing it with gravitational field strength. We know that the Earth has a radial gravitational field. All masses that are attracted to the Earth are pulled towards the centre of the object, and we can use field lines to show the direction that any test mass would be pulled in and experience a force. On a small scale, this field becomes uniform, and any mass, whether it is high or low on this scale, experiences the same force pulling it down towards the centre of the Earth. The same is true for electric fields. A negatively charged particle has an electric field around it. The direction of these arrows shows the direction of the force that would be exerted on a positive test charge placed inside this field. Here we have a plate that is raised to a negative voltage. If we put another plate here and set that to 0 volts, then you'll get a uniform field between these plates. And a positive test charge inside would experience a force towards that negative plate. This is very similar to gravitational fields. However, gravitational fields are only attractive. Electric fields can also repel. If we have a look at a positive charge, then the field lines come out from the centre and just as before, if you were to put a positive test charge within this field, these lines are showing the direction of the force that would be applied to that positive test charge. If we create a positively charged plate, then the electric field would go in the other direction. We can also have combinations. Here we have a positive charge and a negative charge. The field lines would look something like this. And if you have a uniform field with a positive voltage and a negative voltage, the field lines would flow from positive to negative. And any test charge placed in this field would be repelled from the positive and attracted towards the negative, experiencing a force in the same direction as the field lines. If you have like charges, for example, 2 positives or 2 negative charges, then the field lines would repel one another. This field line would look something like this, and you would actually have a spot exactly in the centre, assuming that these two charges have the same amount of charge on them. There would be a spot exactly in the centre where the fields cancel each other out, and we have no field at all. And then we have the same shape, but the arrows are pointing in the opposite direction for these negative charges. And again, there would be a spot in the centre where the electric fields cancel out. Here is a practical technique that you can use to explore field patterns. If we have 2-point charges and a field pattern between them, we can use our previous understanding to work out what that pattern will look like. Or we can do it a practical way. If you were to place an electrode with a negative charge at that location and a positive electrode at this location, then you can use conductive paper to measure the electric field pattern. And what this involves is connecting these two electrodes to a power supply. Here are the wires to illustrate what I mean. So this might be a nail connected to a negative terminal and the positive terminal of a power supply. This is conductive paper, paper covered with a thin layer of carbon so that electricity can flow across the surface of the paper. Once you've got those electrodes set up, then what you can do is you can take a probe from a multimeter, which will often consist of a sharp pointed metal end and then a plastic handle that connects to the multimeter, and you can touch it to these individual points across the surface of the paper and write down what the voltage is at any one location. If this negative voltage was, let's say, -10, and the positive voltage was +10, then you would be recording exactly in between 0 volts at this location here. And in between here, you would be expecting to record -5, and over here, +5, etc. You should be able to get values for every single location across the whole of this grid. And when you do so, you will be able to connect together the locations where those numbers are the same. Locations of equal voltage. The field lines would then cut through these at 90 degrees, and you can recreate the field pattern as it actually appears in a practical experiment. If we recall gravitational field strength, it's defined as the force per unit mass. Mass, because that is the property that gravity acts upon. Any field strength is going to take this structure in its equation. So let's look at electric field strength. Electric field strength has a capital E, and again is the force per unit charge, because charge is what electric fields act upon. If we have a look at the units, then we can derive another equation. Let's start with force. We know that work done is equal to force times by distance. If we rearrange for force, we get work divided by distance. Force per unit charge. The units therefore for this must be joules for work. We have distance, which is measured in meters, and coulombs. Now, joules per coulomb is another way of saying volts. So volts per meter, or voltage per distance, is another way of calculating the electric field strength. And this works for a uniform electric field. So in this uniform electric field, the value of E is constant no matter where you are between these plates. You can be close to the positive terminal or close to the negative terminal or exactly in the middle. This value for E will be the same everywhere, and it depends upon the voltage difference between the plates and the distance apart that they are. So for example, if this was negative 100 volts, and this was positive 50 volts, and they were 5 centimeters apart, then the value for the electric field strength everywhere between these plates would be equal to the difference between the voltages divided by the distance apart, or 3000 volts per meter, which can also be written as 3000 newtons per coulomb. In the same way that when you are discussing gravity, you can say that gravity is 9.81 newtons per kilogram, or 9.81 meters per second squared. We can also rewrite this equation and force times distance is equal to the work done. If we consider a gravitational field and a mass inside that gravitational field, we know that the amount of gravitational potential energy an object has depends on its height above the Earth. We know that if the object moves downwards, the amount of energy decreases, and if that object is being raised, then that gravitational potential energy is going to increase. The same thing happens inside an electric field. Work is done when you change the location of the charge and the voltage that it is exposed to. In terms of electric fields, if you have negative 10 volts at the bottom and positive 10 volts at the top, then there are locations of equal voltage across this space. Exactly halfway across, that voltage will be 0. Here it will be minus 5 volts, and here it will be plus 5 volts as we progress from 10 to 5 to 0, minus 5, down to negative 10. And the electric field lines cross these at 90 degrees. As this voltage changes, work is being done. For example, if you have a positive charge and a negative charge, then this negative charge will be repelled from the negative plate and attracted towards the positive plate. The electric field is doing work on the charge to move it, and it would require work to be done pushing it in the opposite direction to keep it steady. This positive charge is being repelled from the positive plate and attracted to the negative plate. Work is being done to pull it in this direction. The amount of work being done is the amount of voltage that it is moving through, multiplied by the charge of the object. If you have a look at the AQA A-level specification, you'll notice that for this topic, it specifies that this is an A-level only topic. Now, all of these A-level only topics have something in common. They combine AS knowledge with new learning. So, for example, there is a very common style of question for this topic, and that is that a charged particle is fired into a region where there is an electric field. As it enters this region, it will experience a force either upwards or downwards. And this force can be shown to be equal to this, which is the electric field multiplied by the charge of the object. This comes from rearranging this relationship. The AS physics previously learned tells you that force is also equal to ma. So we now have a new relationship that we can link to previous learning. If the electric field did not exist, then the object would continue in a straight line. But because this field does exist, the object is going to be deflected. From its original path. If it's a positively charged object, then it will be attracted towards the lower plate and it will be deflected downwards. A common question is to ask you to calculate this displacement, this vertical displacement. As the object moves across the space and comes out the other side, so here it is at this position, in the middle, and then out the other side, we can also consider that it has the same horizontal velocity all the way through, and as it is accelerated towards the negative plate, it gains a vertical velocity. If we draw the resultant velocity, we can see that this changes across the space as well. And another question that might be asked is, what is the magnitude and the direction of this resultant velocity? Let's go through a worked example so that we can see how we can combine concepts of Newton's laws and also SUVAT with this new electric field understanding in order to solve a problem like this. Okay, so here is a pretty typical setup. We have charged plates with an electric field between them. We have a charged particle entering this space, and if the electric field was not there, it would continue on its initial trajectory. We're given the velocity in terms of the speed of light, and we're given the dimensions of the space with the electric field. And in the question we are asked, what is the magnitude of the resultant velocity and the angle? So we can already see that this is a negative charge, so it's going to be attracted to and repelled from those plates. So the resultant velocity is going to be in that direction, and this angle from its initial direction is what we need to calculate. We're going to be using some new A-level only learning, and we're going to be combining it with a lot of AS level learning as well. And that's what makes the A-level content so much different from the AS, is that you're starting to combine all of these topics together in order to solve problems. We're also going to be using SUVAT. So your mechanics, or in fact all of your AS material, needs to be very strong in order to successfully progress and be successful at the A-level only material. So let's complete this idea over here, and then I'll do my working in orange. This will be a multi-stage calculation. You need to have a very good technique with your working to keep track of the answers that you've got so far, and to show yourself and the examiner the way that you have solved the problem. You need to keep track for yourself, because in an exam condition, when you're checking your working at the end, you need to be able to check your work, not repeat your work. So you need to show what was done in a logical sequence of steps so that you can more easily check that each individual step was correct. So we have our charged particle. This charged particle is going to be attracted to the upper plate, and it's going to be accelerated upwards. The acceleration will only happen while it is inside the electric field. So we need to work out how much time it's experiencing the electric field for. In order to work out that amount of time, we need to know how long the field is and how quickly the charge is moving through it. So we can start off with a very simple AS level equation. The amount of time that the charge is inside the field for. The horizontal distance is 5 centimeters, and the speed is 0.1 times the speed of light, or 10% the speed of light. So I could calculate that separately, or I could just put it into the equation. I always prefer the latter because you can see where the numbers have come from. So it's inside the field for a very short amount of time. The voltage difference between the two plates is one of the numbers take away the other. When you take away a negative, you add. The charge on the object is given as 1 electron's worth. Remembering that negative, because it's an electron, not a proton. The distance between the plates. Notice that I'm not converting, I'm not writing 0.02, because this is easier to trace where it came from. And when you're checking your work, it's easy to make a mistake with the number of zeros. It's actually more difficult to make a mistake when you're just replacing the prefix with what the prefix means. This gives an acceleration of 2.2 times 10 to the 15 meters per second squared. So we have a very short amount of time, but we have a very large acceleration being applied. The negative sign allows us to understand the direction, but we automatically understand the direction here. Oh, it's not that way, it's actually this way, because it's a negative charge being applied to a field with a positive plate. It's going to be attracted to that positive plate. So we know the direction is upwards, and from now on I'm just going to use the magnitude of that acceleration. So we want to calculate that vertical velocity, which is acceleration multiplied by the time. And there we have it. It's now just geometry. So if we have our electron, we know that it's got horizontal velocity of 10% the speed of light, and it also has a vertical velocity of this value. All we have to do now is use Pythagoras to calculate the resultant and trigonometry to calculate that angle. And those are my answers.